Okay, we get to have a little fun this time. We're talking about the different models that we use logarithms or exponentials for. So just kind of real-world applications, if you would. And we'll start with exponential growth, and we've already seen one of them, where we had the interest compounded continuously. A is equal to PE to the RT. So that is describing exponential growth, and we'll see that this really can pertain to the more general y is equal to a e to the RT for any exponential growth. So you'll see there'll be a lot of those actually. Another place that it pops up, an exponential growth, is what's called Moore's Law, which I want to talk about just a little bit. And it's kind of funny, it's more of an empirical law. It's something that was noticed. Mr. Moore is a big shot at Intel. They make the chips and everything, and they were looking at actually the number of transistors on the integrated circuits. And they found, and this is what makes your processing speed on your computers, it affects how much memory you can have, it affects how many pixels on certain things. So it's important to us, so we like more transistors are better. And what he found a long time ago was that it seemed that every 2 years the number of transistors doubled. So it sounds like exponential growth. And what's really crazy is it really has held. Nobody really thought that this could really hold, because imagine exponential growth and how much more transistors we're fitting now than we were years and years and years ago. Exponential growth is enormous. So it's quite stunning that Moore's Law is actually holding up. And to imagine if it's going to continue to hold up, then we need some new technology to figure out how to fit these more transistors on the circuits. So it's probably quantum computing, we don't know, but it's sort of fun to think about it. So anyways, you could imagine if the number of transistors doubles, I could write something like this: doubles every 2 years, I'd say T over 2 then. So that's how I could translate Moore's Law, that the number of transistors doubles every 2 years. Another fun place where we can see exponentials is warp speed. So if any of you guys are fans of Star Trek, they have warp factors. And it turns out that your speed, okay, if we let c equal the speed of light, and I know there's all kinds of things going on outside the window. C is the speed of light, and essentially it's amazingly close to 3 times 10 to the 8th meters per second. So pretty darn fast. Goes pretty far in just 1 second. But if you're saying, Captain Kirk's up there and he says warp factor 2, what does that mean? Well, your speed, as measured in this way, is actually 10 to the warp factor times the speed of light. So you're actually exponentially growing your speed each warp factor. So if he says warp factor 2, your speed would be 10 to the second times the speed of light. So you're going 100 times the speed of light already just at one warp factor 2. So if you wanted to continue that, you could call that 3 times 10 to the 10th meters per second. Now we can certainly do population growth. And a lot of bacteria, things like that, will grow exponentially. Fruit flies, which is often studied, can also, let's say we had a problem, let's actually calculate a problem this time that said you had, after 2 days, you counted the number of fruit flies that you had, and you found you had 100 flies. And after 4 days, you went and counted again, and you found that you had 300 flies. The question would be, could you predict how many would be there after 5 days? Okay, so we know we are expecting these are population growth is exponential, so we're going to start by writing the model A e to the b t. Let's use t for time, measured in days. So what I'm going to do is I'm going to put in the variables that I know, the known values. So I know I have 100 flies. I don't know this value for A. E is, of course, the natural base. I know that number. I don't know B, and I know that it's 100 over here when the time is 2 days. Okay, so my standard unit will be days. So that's one equation. I can write the other equation using the same technique. 300 is A e to the B times 4. Now what I'm going to do here is really kind of fun. To solve this system of equations, there's 2 equations and 2 unknowns, but it's exponential, so we're not real sure how to go. The trick is to divide one equation by the other equation. When I divide this first equation by the second equation, on the left, 100 over 300, and on the right, some good things happen. The a's cancel. So what we're doing is we're eliminating a variable. So now I have e to the 2b over e to the 4b, but of course I know how to divide these exponentials. I'm going to subtract the exponents. So what do I get? I get 1 over 3 to reduce the left-hand side, and then I have to take 2b minus 4b, so it's just e to the negative 2b. So now I have one equation, one unknown, and I can rewrite this, okay, so I can take a natural log, and the log of 1/3 will equal, the answer to the log is the exponent minus 2b. And it's a matter of solving for b at this point. So b is equal to minus a half log 1/3, which I went ahead and did that, and I get b is 0.55. So I found b. Remember, it's 2 equations, 2 unknowns. I have to still find the value of a. But I'll just go back to this first equation that I had right here. 100 is equal to a e to the 0.55 times 2. And if I solve that for a, 100 over e to the 1.1, I get a is, let's see if I can find it, 33.3. So what I've got is a model that the number of fruit flies is equal to I said it was a e to the bt, and I found a was 33.3 and b was 0.55t. So there's my model for a number of fruit flies, and then the question was, let t equal 5, how many fruit flies were there? Well, 33.3 e to the 0.55 times 5. Let me see if I can figure that out. I'll have to do that again. Let's see. 33.3 second e to the x. It gives me the parentheses. 0.55 times 5. Close my parentheses. 520. Let's round it up because I don't want these little partial flies around here. 521. Okay, so that's the number of fruit flies I'll have after 5 days. Okay, let's just talk a little bit more about exponential decay. We've already done it pretty well. We said the number of grams left of this radioactive material would be compared to what you start with. Using half-life, I'll use a 1/2 T over tau. Remember, tau is half-life. So it's the time it takes for the material to decay to half of how much it originally had been. But sometimes we like to write exponential k in a more standard form, a e to the minus bx. So one thing that's fun to do is to go back and forth between the 2 forms. So if I gave you the half-life is 87.7 years for plutonium 238. So this one actually for plutonium decays very, very quickly compared to the longer plutonium, much, much longer. What I want to do is I want to write this in a more n equals n naught e to the minus RT format. Same idea as this one up here. I've just decided to use t instead of x and r instead of b for my variables. But I'll need to find this value of r, and I'll need to figure that out from the half-life. So what I'm going to do is I'm going to use that half-life as my time. So when my time is equal to a half-life, then the amount that's left is a half n naught. So I started with n naught. After one half-life, I'm down to 1/2 n naught. E to the minus r, and the amount of time that took was the half-life, 87.7. And everything will be measured in years. So this is nice because I don't even need to know the initial quantity. The n naughts will cancel, and I have 1/2 is equal to e to the minus 87.7 r. I'll rewrite this and give a natural logarithm of 1/2 is equal to minus 87.7 r. Divide by the 87.7, and I can figure that out. ln 0.5 divided by negative 87.7, and get a value for r. I'm getting 0.008. So what I can do is I can rewrite this as n is equal to n naught e to the minus 0.008 t. So there's now a new model for the exponential decay of plutonium. And I've really just had to convert this using the half-life. Okay, one of the things we're going to do is learn how to linearize the data. And this is the idea that you're going to take some data values, you're going to plot them, and say, they kind of look like an exponential, but I'm not really sure. And the thing is, our eyeball is much better at seeing lines and making a judgment about, oh yes, that's linear or not, it's not a linear function. So let's see if we can linearize this and see that strong linear graph, so we know we got the right fit for it. So let's take, for example, we have some x and y values. Okay, so I'm going to say 1, 2, 3, 4, and 5. So very simple. And I take the data, whatever it is, 4, 5.5, 8, 13, 20. And you look at this and, you know, even without graphing this, you're looking at it and saying, oh, you know, when I go from here to here, I'm adding a little more than 1. Oh, but then I'm adding a little more than 2. Then I'm adding 5, and then I'm adding 7. So that sort of change between each one is changing. So it's definitely not a linear function yet. Okay, it's not going to be a linear function. But if I'd graphed it, I could come over here, and 1, 2, 3, 4, 5. And then over here I'm going to fit 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I'll start graphing it. You know, let's see. 1, 4, 2, 5, 5, 3, 8, 4, 13, I'm being a little sloppy, 5, 20. You look at that and say, well, you're right, it doesn't look linear, but maybe, just maybe, it could be fitted to an exponential. So I'd like to linearize it and take another look at it in that case. So what I'm going to do is I'm going to erase this. I'm going to start a new column. What I'm going to do is I'm going to start a column for the natural log of y. Okay? So everywhere I have y, I'm just going to go ahead and take the natural log of y. So that's 1.386, 1.705, 2.079, 2.565, 2.999. And if I'm not looking at that anymore, and now if I want to graph the x-axis, this was y. So this is just a graph of y. And this time I'm going to graph ln of y. Okay? So those values only go from 1 to 3. 1, 2, 3. 1, 2, 3, 4, 5. And when I look at those, let's see if I can get halfway decent. Something like that. And you look at those and say, oh, okay, yeah, that sure does look like a line. So what I did was I took the natural log of the y values, plotted natural log of y versus the x values, and now it looks like a straight line. So you can see, wow, there's exponential growth for sure, okay? It really does linearize with the natural log. So it is exponential growth. So now the thing would be to actually fit this line to y equal mx plus b. Your calculator calls it y equal ax plus b. So I'm going to go into my calculator with these in my stat edit, make sure I get all these. I'll show you how to do that again in class. This right here is actually a fun thing you can do in list 3. You can actually tell it to take a logarithm of list 2. So we'll do that in class together. It'll give you all the right data. And then you're just going to do a stat calc. You do the linreg, but you make sure you do L1, comma L3. Okay? When you do that, you're plotting natural log y versus x. So when it returns a and b, it's returning ln y is equal to, and I did mine, and I got 0.4x plus 0.9. So that's the equation of this line over here, okay? That best fits the data, remember? So let me figure out how I'm going to turn that 0.4x plus 0.9 into an exponential growth model. Because right now it's looking like a logarithm and it's not y as a function of x. So what I'm going to do is rewrite this as an exponential. So I'm going to write, instead of ln, I switch to exponential form. The exponent is the answer to the logarithm, and that's going to equal y. So now I have y as a function of x. I'm not quite done because I want to tidy up this exponent a little bit. You remember your rules of exponents. I'll remind you, x squared times x cubed is equal to x to the 2 plus 3. So that's what we've got right here. We've got a plus in our exponent. So I'm going to call this e to the 0.4x times e to the 0.9 is equal to y. Take a minute, make sure you understand that. That's a really key feature right there that's really nice, working on this rules of exponents. I can calculate what this e to the 0.9 is, and I'm going to write it in the front. E to the 0.9 is 2.46. Then I still have the e to the 0.4x is equal to y. And of course we like to write this as f of x a lot of times, so maybe I'll write it this way, 2.46 e to the 0.4x. And that is the exponential model for the data that I had originally had before. So we're good. One of the things we can do with exponentials is what's called the Gaussian distribution. Now, it has a lot of other names. What makes it interesting, it's exponential, but the x is being squared. So things start to become symmetric in x when you square it. And you're always having x squared is always positive, so it's always e to the minus something. So what happens is you get this portion of the exponential, but then you have to have a symmetric, so it starts looking like that. So that's basic graph of a Gaussian. You might recognize this. We've always seen this before and called it a bell curve. Teachers are notorious for trying to grade to a bell curve where you want your C students right here, and then there's some A students, and then there's some D and even F students on either side. And this would be the number of students, right? Receiving, that's a number. And this is grade, so that's kind of a classic curve that we do. Or it can be called the normal distribution, and this is used so often in statistics that it's nice to see it, because you're going to spend so much time with it if you do take a statistics class that I'd love to see you take. Like we said, it is a symmetric curve. So when you're looking at this, the left and right are symmetric. Hi, Caroline, hold on. Okay, so we were talking about this being a symmetric curve because x is being squared. So what's interesting is this sort of maximum right here is occurring right here at the average x value, okay? So that will tell you the maximum number of students are scoring the average grade, okay, and then it curves on either side of that. They do a lot of things with standard deviations with this. Oh, you'll just spend so much time. But what I want you to get out of this is your average, okay, this little location of that average x is going to take place when x is equal to b. So this sort of b here is that shift, okay? It's that shift to the right, b units, because normally this is at x equals 0. If b is 0, we have this sort of center line, okay? So for example, here's a question I could ask you. Y is equal to 3 e to the negative x minus 5 squared. Could you find the x and y value for the average of this function? Okay, so what I would do is say, well, the average is going to happen when x is equal to 5, because that's this number here. And then I just have to figure out what the y value is. And, well, if x is 5, then all of this is 0. E to the 0 is 1, so y is equal to 3. So I'm at 5, 3 is the location of this point right here, the maximum. So the maximum of the function is 3 when x is 5.